So sharp at 2 o'clock we'll start the session. Just ask your friends, those who have not joined. So today we are going to take important algorithm from Deadlock, that is Banker's algorithm. Okay. So yesterday we discussed about safe state and unsafe state. So we started the second method. So second method under methods for handling deadlock, that is deadlock avoidance. So yesterday we discussed first method, deadlock prevention, and we started deadlock avoidance. So in a deadlock avoidance, we discussed the concept of safe state and unsafe state. So safe state, the state in which safe sequence is followed. The state system follows the state in which safe sequence is followed by the system. So it is called as a safe state and unsafe state. So when the system is going to the unsafe state, if system is following unsafe sequence. So accordingly, yesterday we discussed with the help of example what is safe state and what is safe unsafe state. So unsafe sequence and safe sequence. So if system follows safe sequence, we can say that system will be in safe state. And if system is following unsafe sequence, so we'll see that definitely the system will be going into the deadlock state. So that we discussed with the help of example yesterday. So today we'll discuss about two algorithms. Actually, under deadlock avoidance, we are discussing about two algorithms. So one algorithm, that is the Banker's algorithm, where we are discussing about the safe sequence. So again, in Banker's algorithm, two sub algorithms are there, and like that. So we'll discuss first Banker's algorithm, then resource allocation graph algorithm. So two algorithms are there. One is Banker's algorithm, another is resource allocation graph algorithm. So we'll discuss this resource allocation graph algorithm after Banker's algorithm. So first of all, we'll switch to the Banker's algorithm. So Banker's algorithm, it is first algorithm in deadlock avoidance. So Banker's algorithm, the resource allocation graph algorithm applicable to resource allocation with multiple instances of each resource type. Okay, let it be. We'll see this algorithm afterwards. So Banker's algorithm is used. Banker's algorithm is used to remain this drawback, that is actually the resource allocation graph algorithm. It is not applicable in case of multiple instances of resource type. So that's why we are taking the help of Banker's algorithm. So in case of Banker's algorithm, in the sense, in the system there are n number of instances of resource type. So in that case, we are able to apply the Banker's algorithm. Okay. So better actually, as we are saying that the drawback of resource allocation graph algorithm is removed, or due to that drawback, we are moving to the Banker's algorithm. So first of all, we'll discuss the resource graph algorithm. So it's a simple algorithm. So all of you listen carefully. This is the first algorithm which we are discussing under deadlock avoidance. Resource allocation graph algorithm. So yesterday we discussed about resource allocation graph, right? We discussed about resource allocation graph. So in the resource allocation graph, we discussed how to represent the processes, how to represent the resources, how the request is made. So it's called as a request age, and how the resource is allocated. It is called as a assignment age. So like that onwards, based upon that resource allocation graph, we'll discuss this algorithm. This algorithm is used for deadlock avoidance in addition to the request and assignment age. In addition to request and assignment age, we introduce a new type of age called a claim age. Actually, in resource allocation graph, we discuss the concept of request age and assignment age. And in this algorithm, along with these two ages, we are going to introduce one more age, and name of that age is called as a claim age. So we'll see what is by claim age. So a claim age, PI, towards RJ. So actually PI towards RJ. So this arrow indicates that PI is requesting RJ. So the claim age PI requesting RJ indicates that process PI may request a resource RJ at some time in future. Actually, PI has not made a request right now to resource RJ, but in future, PI may request resource RJ. Listen carefully. Actually, if the request is made, you can call it as a request age. And if the request is going to made in future, that is after some time, yet request is not made. आता रिक्वेस्ट केलेली नाहीये, थोड्या वेळानंतर रिक्वेस्ट केली जाऊ शकते प्रोसेस पीआय कडून रिसोर्स आरजे ला. सो दॅट इज रिप्रेझेंटेड विथ द हेल्प ऑफ क्लेम एज. म्हणजे मी एक प्रोसेस आहे, मला एखादा रिसोर्स लागणार आहे, तो रिसोर्स आता सध्या लागणार नाहीये, मला मे बी अर्ध्या तासानंतर लागणार आहे. म्हणजे इन फ्युचर मी त्या रिसोर्सला रिक्वेस्ट करू शकते. जर मी रिक्वेस्ट केली, so that age will be treated as a request age, but right now this age is treated as a claim age. Got it? So claim age and request age. What is the difference? Request age indicates that request has made by the process PI to resource RJ. And what about claim age? Claim age tells that process PI may request resource RJ in future. Process PI may request resource RJ in future. Yet PI has not requested, but in future PI may request the resource. So that is represented with the help of claim age. So in this resource allocation graph algorithm, we are taking the help of claim age along with request age and assignment age. Okay. So this is about the claim age, and with the help of that, we are going ahead. So this age resembles a request age in same direction, but is represented by dashed line. Actually, if you observe this figure, so this is the resource allocation graph for deadlock avoidance. So if you consider this resource allocation graph, so over here, two processes are there, P1 and P2, and two resources are there, R1 and R2. And again, it is assumed that R1 as well as R2, they are having only single instances. Only one instances are there with respect to R1 and R2. Okay. So further, resource R1 is allocated to process P1 and process P2 is requesting resource R1. So if we are observing this resource allocation graph, so one request age is there, that is process P2 is requesting resource R1 and R1 is already allocated to process P1, and remaining two ages are there, but these are shown with the help of dashed lines, right? So process P1 to R2. So process P1 to R2, so it is called as a claim age. Again, process P2 to R2, it is also the claim age. So what it indicates? In future or after some time, process P1 may request resource R2. Also, after some time or in future, process P2 may request R2. So these are the two claim ages in this resource allocation graph. Okay. So right now, there is no cycle in this graph. Right now, there is no cycle in the graph. But if somebody makes a request, assume that process P1 makes a request to R2. That is, your claim age will be get converted into request age. लक्ष द्या carefully. If P1 requests R2, आपण काय म्हणलं, आता तर सध्या P1 ने रिक्वेस्ट केली नव्हती, पण थोड्या वेळानंतर P1 रिक्वेस्ट करू शकतो R2 ला. असं अजून करा की थोडा वेळ झालेला आहे and P1 is requesting R2. So this dashed line, dashed arrow from P1 to R2 will be get converted into request age. म्हणजे सॉलिड एज मध्ये तो कन्वर्ट होणार आहे. आता सध्या इनिशियली डॅशड लाईन मध्ये रिप्रेझेंट केलेलं आहे. So if P1 makes request to R2, so that age will be get converted into a request age from P1 to R2, and as R2 is totally free, if you are looking towards the resource, so right now resource R2 is totally free because yet P2 has not made the request, right? So and R2 is also not allocated to any process. So that's why operating system will grant the request of P1. म्हणजे ऑपरेटिंग सिस्टीम काय करेल, P1 ची रिक्वेस्ट ग्रँट करेल. जर रिक्वेस्ट ग्रँट केल्यानंतर काय होणार आहे, so that request age will be get converted into assignment age, right? The request age will be get converted into assignment age, and after converting into assignment age, so if you observe, so there will be the deadlock. So and that is shown over here. So if you observe this, so actually here R1 is allocated to P1. So actually here they considered the request of P2 is granted. आता मी तुम्हाला P1 ची रिक्वेस्ट म्हटलं होतं, पण P2 ची जर रिक्वेस्ट P2 ने रिक्वेस्ट केली आहे instead of P1, assume that P2 has requested, so and the request of P2 is granted. म्हणजे P2 to R2, so whatever the dashed arrow is there, that will be get converted into solid arrow, that is request age. And after some time that request is granted by the operating system, so that request age will be get converted into assignment age, right? So that is arrow will be from R2 to P2, right? And that is shown over here, that is shown over here. So what happens if you observe this diagram? So over here cycle is going on, right? Cycle is observed provided that P1 will request R1 in future. So if P1 requests R2 in future, so there will be the cycle and there will be the deadlock. So if this conversion is done by the operating system, so the system is going into the unsafe state. System is going into the unsafe state. जर ऑपरेटिंग सिस्टीम न P2 ची रिक्वेस्ट ग्रँट केली तर काय होणार आहे, ऑपरेटिंग सिस्टीम or these two processes, they are going into the deadlock state, right? Or if you consider P1, so in case of P1 also, so if P1's request will be granted, if P1's request will be granted, that is R2 will be allocated to P1 and R1 is also allocated to P1. So in case of that, deadlock will not be there. Are you getting my point? So in this example, instead of granting the request of P2, so operating system should grant the request of P1. But again, it totally depends upon the request. Jar P1 ne request पहिल्यांदा केली, if P1 does the request first, so system will be in the safe state, and if P2 does the request first, so system will be in unsafe state. So got the clear idea? Yes, students, are you listening to me? Hello. Hello, students, are you there? Hello, am I audible?
Yes, ma'am.
See, only 38 students are there. Okay, so any doubt about this resource allocation graph algorithm? So got the clear idea about claim age? Got the clear idea about algorithm? Yes?
Yes, ma'am.
Okay, so very simple algorithm is there. Only along with assignment age and request age, we are introducing one more age called as a claim age, and that claim age is represented with the help of dotted lines, dotted arrow, and that dotted arrow indicates that in future that process may request that resource after some time or in future, and if that request is granted, so it depends upon the situation. So in this situation, if the request of P2 is granted, so system is going into the deadlock state, and if the request of P1 is granted, so system is not going into the deadlock state, it will be in the safe state. So this is about the first algorithm, resource allocation graph algorithm, but the limitation of this algorithm is that, so this algorithm is applicable only to the single instance of resource type. System मध्ये जर resource type चे एकच instance, single instance असेल तरच हा algorithm apply करू शकतो आपण. Otherwise, if there are multiple instances, we are unable to apply this algorithm. आता इथं असं अजून केलेलं की या डायग्राम मध्ये R1 चा पण एकच इन्स्टन्स आहे, एकच R1 आहे आणि एकच R2 आहे. So actually we have not shown over here the dot inside the square, but by default if we are showing only square, it indicates that only one instance is there with respect to that resource type. So if there will be the multiple instances of the resource type, so this algorithm is not applicable. So this is the major drawback with respect to this algorithm. Okay, so just note it down. I hope you have noted it. This one, the point deadlock avoidance. Under that, the concept of safe state, unsafe state. In your notebook, you can just note it down: safe state, unsafe state, and in front of safe state, so system which follows safe sequence is called as a safe state, and in front of unsafe state, system which follows unsafe sequence is called as a unsafe state. Okay, and below that, yesterday's example, you can note it down. So yesterday we taken this example, how to determine the safe sequence. So you may take this example. Consider a system with 12 magnetic tape drives and 3 processes P0, P1, P2. So process P0 requires 10 tape drives, process P1 requires 4 tape drives, process P2 requires 9 tape drives. Suppose at time T0, process P0 is holding 5 tape drives, process P1 is holding 2 tape drives, and process P2 is holding 2 tape drives. Accordingly, according to this situation, so you have to show the table. What is the maximum need of each process? What is the current need of the process? So note it down. Note this example in your notebook. So all the students, you can convey the message to your friends, those who are absent. So it may affect on your attendance. If your attendance is below 80%, so again we have to think about your terms, ISC's marks. So we are unable to send the ISC marks also if your attendance is below that criteria, that is 80%. So keep in mind. So your attendance should be minimum 80%. If we are sending the ISC marks, so along with ISC marks, we have to send the attendance also to the university. So if the attendance is below 80%, so university is not accepting your ISC marks, and it may indicates that as a backlog with respect to that subject. So take note of it. Maximum students, they are remaining absent for the lectures. I am observing from last 2 lectures. So attendance is very less. Okay, note down this example. And here we have noted it down: number of processes, maximum need of each process, current need of each process, total number of available resources with the system. So out of 12, total 9 are allocated currently and 3 are available, and accordingly we determined the safe state, safe sequence. So safe sequence with respect to this example is P1, P0, P2, and as 3 processes are there, so total six sequences will be there, and out of that 6, only one is safe, and remaining 5 are unsafe in this example. So yesterday we taken this example. So hope you are understanding it. Just write the safe sequence. Now write down the first algorithm under deadlock avoidance, that is resource allocation graph algorithm. Note it down. This algorithm is used for deadlock avoidance. In addition to request and assignment age, this algorithm introduces a new type of age called as a claim age. Meaning of claim age is given over here. A claim age PI to RJ indicates that process PI may request resource RJ after some time or in future. This age resembles a request age in same direction but is represented by dashed lines. The direction of the arrow is same like a request age. Only the difference between request age and claim age is age is shown with the help of solid line and claim age is shown with the help of dashed lines. This is the sample example of a resource allocation graph having claim age. Draw this diagram. Suppose that process PI requests resource RJ. The request can be granted only if converted the request age to an assignment age. Request can be granted only if converting the request age to an assignment age. So if we assign resource R2 to P1, it will not go into the cycle, it will not form the cycle. And if no cycle exists, there will not be the deadlock. The system will be in the safe state. If cycle found, then system indicates that it is going into the unsafe state. Accordingly, we draw another diagram, second diagram, assuming that process P2 requested R2 and that request is granted, and that's why that request age is get converted into assignment age. So first of all, claim age from P2 to R2 is get converted into request age, and that request age is get converted into assignment age. So we got this resource allocation graph where we are getting the cycle. So in future, if process P1 requests R2, so there will be cycle and there will be the deadlock. This is the unsafe state. So that's why if you think about this example, the operating system should grant the request of P1 and should not grant the request of P2. If it grants the request of P2, it is going into the deadlock state, and if it is granting the request of P1, so it will not be going into the deadlock state, it will be in the safe state. So draw this diagram also. This algorithm is totally based upon the resource allocation graph having claimage. And we should know how the claimage is get converted into request age and how the request ages get converted into assignment age. Over. Yes, students. Actually, yesterday I have posted this PDF file on your group also, so you can refer that file also. So better I request all of you. So whatever notes I'm sharing on the group, so I'm sharing to the students also, those who are requesting. So actually, these are somewhat big files, and that's why it is somewhat difficult to post on the group. So if you want, you can just drop a message to me along with your email ID. So I will mail all these notes to you also, so you can refer by your own, or within yourself you can circulate the notes, those who are getting from me. Okay, so this file I have posted on the group yesterday, so you can just take it and better keep it with you, save in one of the folder on your desktop or on your laptop, so that it will be better for you to refer it in future. Okay, so now come to the part of bankers algorithm. So the drawback of previous algorithm, that is the resource allocation graph algorithm, is that so that algorithm is applicable only in case of single instance of resource type. So if system consists of single instance of resource type, then only we are able to apply that algorithm. Otherwise, if there are multiple instances of the resource types, so we are unable to apply. Okay, so like what are my instances? So I am having 12 printers. So resource type is printer and instances are 12. So if 12 printers are there and 2 processes are there, so I am unable to apply the resource allocation graph algorithm, because it is applicable only if the number of instance is equal to 1. That is only one printer, right? So if there are multiple instances, so in that case we need to apply the second algorithm, that is the banker's algorithm. So the resource allocation graph algorithm is not applicable to a resource allocation system with multiple instances of each resource type. So that's why we are going ahead to the banker's algorithm. So listen carefully, this is very popular algorithm and somewhat difficult to understand. So actually, we discussed yesterday two examples which are very simple, and I said that if you got these examples, you will be able to understand the further algorithms. So based upon that example, we are going ahead over here in the banker's algorithm. So banker's algorithm is used to remove this drawback, but it is less efficient. Actually, it is less efficient. It is not more efficient. So how it is less efficient, we'll see with the help of example than the resource allocation graph scheme. So the name was chosen because this algorithm could be used in a banking system to ensure that the bank never allocates its available cash in such a way that it can no longer satisfy the needs of all its customers. So normally you all are familiar with banks. So बँक असं कधी करत नाही की जेवढा अवेलेबल मनी आहे बँक मध्ये तो सगळाच देऊन टाकत नाही. So it keeps some part as a reserve, so that that will be used to satisfy the few more customers, or the customers which are coming daily. So bank is not giving all the money to only one customer. It keeps some money as a available money which will be used in future. So in the same fashion, that's why the name of the algorithm is banker's algorithm. We'll see how the banker's algorithm works over here. So when a new process enters the system, it must declare the maximum number of instances of each resource type that it may need. So the basic requirement in Banker's algorithm is that whenever any new process enters in the system, so that process should declare how many number of maximum resources it requires for execution. That is the basic requirement. So further in this algorithm, we are using total 4 data structures, and these data structures are nothing but first one, name of the first data structure is available, second one max, third one need, and sorry, only 3 data structures we are using. Just a minute, need, max, something is missing. Actually, 4 are there. So I'll take the help of, okay, yeah, yes. So these are the data structures. One is allocation, another is max, another is available, and fourth one is the need. So here I have written the columns: allocation, max, available, need. These are the 4 data structures which we are using in this algorithm. So we'll see the available, that is nothing but available number of resources with the system. So it is also represented as available of J is equal to K. So there are K instances of resource type Rj are available with the system. Listen carefully to understand the concept. So how the available is represented? So available of J is equal to K. So K indicates number of instances of resource type J. And these many number of instances are available with the system. Okay, so yes, you can take the yesterday's example. So yesterday, whatever example we considered, that is total 12 printers were there. Out of that, 9 were allocated and 3 are there with the system. So that 3 represents K and printer represents J over here. Okay, so available of J is equal to K indicates that K number of instances of resource type J are available with the system. Next, max. It is the maximum maximum requirement of the process, and it is represented by max of Ij is equal to K. So K instances of resource type J are required maximally by process Pi, or process Pi requires maximum K instances of resource type J. Process Pi. So I represents process, J represents resource type, and K represents number of instances. So how to read this? Max of Ij is equal to K. So process Pi requires maximum K instances of resource type J. Maximum K instances of resource type J. Okay. Next, that is according to our yesterday's example. So we taken the first process, that is process P0. With process P0, 5 printers were there and 5 more it was in need. So that's why its total maximum need is 10. So 10 printers are required by process P0 to complete its execution. So this is the maximum need of that process P0. Okay. So like that. Next is the need. Actually, one more is missing over here. So after max, that allocation is there. So allocation is nothing but allocation of Ij is equal to K. Allocation of Ij is equal to K. Here it is given. So allocation of Ij is equal to K. It indicates that K instances of resource type J are allocated to process Pi. K instances of resource type J are allocated to process Pi. Okay, so this is about allocation, and the last one is the need. So these are the data structures. So these are the tables. These are the matrices where we are keeping the information about the resources and processes and number of instances. So need is calculated. So need is nothing but max minus allocation. So it is the need. So process P0 was in requirement of maximum 10 printers. Process P0 la त्याचे ऑपरेशन कम्प्लीट करण्यासाठी मॅक्सिमम 10 प्रिंटर लागणार होते, त्यापैकी त्याला 5 अलोकेट केलेले आहेत आणि अजून किती लागणार आहेत त्याला, अजून 5 लागणार आहेत. हाऊ मेनी मोर इट नीड्स, so that is calculated max minus allocation, that is 10 minus 5 is equal to 5, so need will be 5, right? Or you may take the third process according to our yesterday's example. So third process, its maximum need was I think 9, and 2 were allocated to it and it was in need of 7 more, so that's why the max will be 9, allocation will be 2, so need will be 9. So like that we have to calculate need. So need is equal to max minus allocation, and need of ij is read like need of ij is equal to k. So k instances of resource type j are needed by process pi. K instances of resource type j are needed by process pi to complete its execution. So this is about need. So these are the 4 data structures which we are using inside this algorithm. Okay. So now come to the part under Banker's algorithm. Again 2 algorithms we are discussing based upon these 4 data structures. म्हणजे बँकर अल्गोरिदम, बँकरचा अल्गोरिदम हा एक अल्गोरिदम नाहीये, याच्यामध्ये 2 अल्गोरिदम आहेत, and in these algorithms we are using these 4 data structures. Okay, so first of all we'll discuss about the first algorithm, and the name of the first Banker's algorithm is the safety algorithm. Name of the first Banker's algorithm is safety algorithm. So again safety algorithm, it determines the safe state. The algorithm for finding whether or not a system is in a safe state or not. So with the help of this algorithm, what we are doing, so we are just we are determining whether the system is in safe state or in unsafe state. Okay, in the sense, in turn we are determining the safe sequence and unsafe sequence. Okay, so this is the algorithm, this is the safety algorithm. So it is the 4-step algorithm. So let work and finish be vectors of length m and n respectively. So I hope everybody is listening to me. All of you are listening to me. So this is the 4-step algorithms. So steps are given one by one. This is the first step. Let work and finish be 2 vectors of length m and n respectively. Initialize work is equal to available. So whatever available is there, so that we need to assign to work, and finish of I. So finish of I is equal to false. So this finish of I indicates that I is nothing but the process. So I finish of I is equal to false for I is equal to 1 to n. So initially before system starts, so each and every process is not finished, right? Initially कुठलीच प्रोसेस कंप्लीट झालेली नसणार आहे, त्यामुळं सगळ्यांचा फिनिश फॉल्स असणार आहे. So false of I is equal to finish, sorry, false of finish of I is equal to false for all the processes. So I ranges from 1 to n, and however the resources will be get allocated to the processes, so process is going to finish, and then finish of I becomes true, right? So this is the first step. So find an I, this is the second step. Find an I such that both finish of I is equal to false and need of I is less than equal to work. आपल्याला अशी प्रोसेस फाइंड आउट करायची आहे. सो आय इंडिकेट्स प्रोसेस. सो फाइंड अन आय सच दॅट त्या आयचा ती आय फिनिश पण झालेली नसणार आहे. फिनिश झालेली असेल तर त्याचा फिनिश ऑफ आय ट्रू असणार आहे. झालेली नसणार आहे म्हणजे त्याचा फिनिश ऑफ आय फॉल्स असायला पाहिजे. ओके, सो फाइंड अन आय सच दॅट बोथ फिनिश ऑफ आय इज इक्वल टू फॉल्स and its need of I is less than work. Okay, so what is work? Work is nothing but available. So whatever need is there, so need should be less than equal to available, right? So then only you have to choose the process, otherwise you have to leave that process. Okay, so if no such I exist, go to step 4. जर अशी I present नसेल सिस्टीम मध्ये तर डायरेक्टली चौथ्या स्टेपला जायचंय. Otherwise you can go to the third step, and the third step is nothing but work is equal to work plus allocation. Third step is equal to work plus allocation. फिनिश ऑफ आय इज इक्वल टू ट्रू. तर तिसऱ्या स्टेप मध्ये असं अजून केलेलं आहे की दुसऱ्या स्टेप मध्ये आपल्याला तशी आय फाइंड आउट झालेली आहे, म्हणजे ती कंप्लीट झालेली नाहीये आणि त्याची नीड वर्क पेक्षा लेस आहे. तर त्या केसमध्ये काय करणार आहोत आपण, त्याची नीड आपण भागवणार आहोत, म्हणजे त्याला लागणारे रिसोर्सेस त्याला देणार आहोत आपण त्या प्रोसेसला. अँड दॅट प्रोसेस गोज फॉर कम्प्लिशन, अँड आफ्टर कम्प्लिशन दॅट प्रोसेस विल रिलीज ऑल द रिसोर्सेस, अँड दॅट इज डन इन थर्ड स्टेप. सो इन द थर्ड स्टेप वर्क इज इक्वल टू वर्क प्लस अलोकेशन. जेवढे काय अलोकेट केले होते त्याला रिसोर्सेस, ते सगळ्या प्रोसेस रिलीज करणार आहे. अँड आफ्टर रिलीजिंग these resources will be get added to the work that is available, and finish of that I will be becoming true, so indicating that that process is get finished according to the previous example. जे yesterday आपण example discuss केलेलं आहे. So based upon that example I am discussing this algorithm. So go to step 2, that is if one process is finished, again go to step second. So again find out the next I. Again if you found such I, so complete the third step, again go to the second step. So like that we are looping in third and second step. And when we are going to the fourth step, if we are not finding such I, so if finish of I is equal to true for all I, done the system is in a safe state, right? जर सगळ्याच I चा finish true झाला असेल, so what it indicates, all processes get finished. So it indicates that process is in the safe state. In turn, we are getting the safe sequence. So this is the algorithm. So only algorithm, theory algorithm, it is quite difficult to understand. So we'll take this algorithm and we'll discuss this algorithm with the help of our previous example first, and then we'll go to the next example. So this is somewhat complicated example. आपलं मागचं एक्झाम्पल होतं, कालचं एक्झाम्पल घ्या. कालच्या एक्झाम्पल मध्ये आपण घेतलं होतं टोटल प्रिंटर किती आहेत. Come on, I hope you are listening to me. Yesterday's example, how many total printers are there in the system? Come on students, are you listening to me? Hello, unmute yourself. Okay, so yesterday we taken total 12 printers, right? How many processes were there? Three processes were there, that is P0, P1 and P2. Okay, so how many printers are allocated to P0? P0 ला किती प्रिंटर दिले होते सिस्टम ना? So this file is there with you, you can look inside that file. ही PDF तुमच्याकडे पण आहे. Come on, P0 ला किती प्रिंटर दिलेत सिस्टम ना? 5. Good. P1
2.
P2 2. Okay, and how many printers are available with the system now? 3. Good. So total 12 there, and out of 12, 5 plus 2 plus 2, that is total 9 allocated by the system to process P0, P1 and P2. So now available are 3. Okay, so now what is the need of P0? P0 ला कंप्लीट होण्यासाठी अजून किती प्रिंटर लागणार आहेत? How many printers are required by process P0 to complete its operation?
5.
5 more are required. P1 requires
2.
And P2 requires
2.
P2 requires
7.
7. Good. So this 5 to 7, this is nothing but the need. Okay, and this 5 to 2, this is the allocation. 5 to 2, it is the allocation, and this 5 to 7, it is the need. And what is the max? Max is nothing but 10, 4 and 9. So max is 10, 4, 9. Allocation is 5 to 2, and from the max and allocation we calculated the need 5 to 7. Okay, so now come to the algorithm. So we'll follow the algorithm based upon this one, because yesterday we calculated the shape sequence. So let work and finish be vectors of length m and n respectively. Initialize work is equal to available. So now what will the work? Come on. Work is equal to available. What is available? Available is nothing but available number of resources. किती resources available आहेत सध्या सिस्टीम कडे? 3. Okay, so here work becomes 3. Okay, so work is equal to 3 and finish of I. So finish of I. So we'll take according to our example, I's value varies from 0, 1, 2. Right? So finish of 0 is equal to false. Finish of 1 is equal to false and finish of 2 is equal to false. आपल्या एक्झाम्पल मध्ये 3 प्रोसेसेस आहेत, त्यामुळं आणि त्या प्रोसेसला आपण नाव पण दिलेले आहेत P0, P1, P2. So that's why the value of I will be 0, 1, 2. So finish of 0 will be false, finish of 1 will be false, finish of 2 will be false. So this is the initialization. This is the first step. Now go to the second step. Find an I such that both finish of I is equal to false and need of I is less than equal to work. Okay, so आपल्याकडे 3 प्रोसेसेस आहेत आणि तिन्ही प्रोसेसेसचा फिनिश ऑफ आय फॉल्स आहे. So this first condition is true for all 3 processes. What about the second condition? So second condition is need of I less than equal to work. So which process satisfies this condition? Can anybody tell me? Which process satisfies this condition? Need of I less than equal to work. Work is 3. Come on.
P1.
Good. What is? See, need of P0 is 5, need of P1 is 2, and need of P2 is 7. So which process need is less than work?
P1.
Good. So P1's need is 2. P1's need is 2, which is less than equal to work. Right? Work is 3. So that's why according to our shape sequence in our previous example, we choose the P1 first. Shape sequence मध्ये पहिली प्रोसेस कुठली चूज केली आपण? P1 चूज केलेली आहे. Right? So we found आपण P0 नाही चूज केली, दुसऱ्या स्टेप मध्ये आपण P1 चूज केलेली आहे. राईट? जर P0 चूज केलं तर काय करायला लागेल? P0 मध्ये सेकंड कंडिशन सॅटिस्फाय होत नाहीये. B condition satisfy होत नाही. So that's why we are unable to choose P0. So we have to go to the next process. Next process is P1 and P1 satisfies both these conditions. So that's why in our shape sequence, first process will be P1. So after P1, so that is after second step, what we are doing? We are going to the third step. सेकंड स्टेप जर सॅटिस्फाय होत असेल तर आपण तिसऱ्या स्टेप मध्ये जाणार आहोत आणि तिसऱ्या स्टेप मध्ये काय करतोय? वर्क इज इक्वल टू वर्क प्लस अलोकेशन. सो व्हाट वाज द वर्क आफ्टर अलोकेटिंग 2 प्रोसेस P1? प्रोसेस P1 ची नीड होती 2, सिस्टीम कडे अवेलेबल होते 3. मग त्या 3 मधनं 2 अलोकेट केले म्हणजे सिस्टीम कडे राहिले किती? 1. राइट? सो वर्क विल बी 1. And what is the total allocation to process P1? It's 4. अगोदर 2 दिले होते आणि आता 2 दिले आपण process P1 ला. And its maximum need was 4. So as its maximum need is satisfied, so process P1 goes for completion. Process P1 goes for completion. Process completes, P1 will be get completed, and after completion process P1 will release as 4, and these released 4 will be get added in the work because this is the available with respect to the system. So that's why now work becomes 5. Now work becomes 5 and finish of I is equal to 2. So what is I? I is nothing but our process 1, P1. So P1 finish of 1 will be 2. So P1 is completed. Okay, again go to step 2. So again we are coming to next step. Now the available, that is work is 5. Work is 5. So which process we are able to choose? Come on.
P0.
P0. Good. So we are able to choose P0 because P0's need is 5. We cannot choose P2 because its need is 7, which is greater than work, right? So that's why we are unable to choose P2. We are able to choose P0. So that's why in our safe sequence, the second process will be P0. First process will be P1 and second process will be P0. So again, 5 were available. So we allocated 5 to process P0. Now process P0 is having total 10. So maximum need is satisfied with respect to P0. P0 goes for completion and process P0 releases all these 10, and now available will be again 10. Available will be again in 10. So what we are doing, that is we by default we satisfied the process P0. After process P0 work becomes 10. That is work, initial work was 0 plus 10. So it becomes 10. So finish of 0 becomes true. So P0 is also completed. Again go to step 2. Now work is 10. So you have to find out an I such that need of I is less than work. And by default we are able to choose the process P2 whose need is 7, which is less than 10. Right? And again from that 10 we are allocating 7 to process P2. Now process P2 is having total 9. So process P2 goes for completion, and it again after completion its finish becomes true and process P2 will releases all 9. So all 9 will be released and that all 9 will be get added into the work according to the third step, and all finish of I becomes true, right? And when the finish of I becomes true for all I, then what we are doing? So we are saying that this is the safe sequence. So what is the safe sequence we get just now? We got the safe sequence P1, P0, P2. So this is the safe sequence, and like that we calculated the safe sequence with the help of this algorithm. So what the clear idea? Yes, students?
Yes, ma'am.
Okay. So first of all, you can just note it down. Okay, so I hope you have noted the first algorithm. So this was the first algorithm. Second algorithm, it is Banker's algorithm. Note it down. So note it down. So why to use Banker's algorithm? What is the drawback of resource allocation graph algorithm? So the drawback of resource allocation graph algorithm will be treated as an advantage with respect to Banker's algorithm. The limitation of Banker's algorithm is it is less efficient. And why the name is given as a Banker's algorithm? Because mostly it is applicable in case of bank. That's why it is called as a Banker's algorithm. So this Banker's algorithm takes the help of 4 data structures. You can just note it down. First data structure name is available. So available of J is equal to K, means K instances of resource type J. are allocated, sorry, available, are available. Second data structure, max of ij is equal to k instances of resource type j. Maximum k instances of resource type j are required by process pi. Okay, and the next one is the allocation of ij is equal to k. So k instances of resource type j are allocated to process pi. You can just try directly write these statements. Allocation of ij is equal to k. So third data structure name is allocation. And last one, need. So need of ij is equal to max of ij minus allocation of ij. Okay, again under safety, Banker's algorithm, we are discussing about two algorithms. First one is the safety algorithm. So right now we are discussing about safety algorithm. So write down the safety algorithm. So this safety algorithm is used to calculate the safe state. And how to calculate the safe state? By calculating the safe sequence. Let work and finish be vectors of length m and n respectively. Initialize work is equal to available and finish of I is equal to false for I is equal to 1 to n. First step. Second step. Find an I such that both finish of I is equal to false, need of I is less than equal to work. If no such I exists, go to step 4. If such I exist, असा आय जर असेल तर आपल्याला तिसऱ्या स्टेपला जायचंय आणि नसेल तर चौथ्या स्टेपला जायचंय. So in the third step, so this is the third step. So work is equal to work plus allocation, finish of I is equal to true, go to step 2. And the fourth step, if finish of I is equal to true for all I, then the system is in safe state. Okay, so based upon this algorithm, now we are taking one more example which is somewhat difficult. Okay, so here consider a system with 5 processes P0 to P4 and 3 resource types A, B, C. Resource type A has 10 instances, resource type B has 5 instances, and resource type C has 7 instances. Suppose that at time T0 the following snapshot of the system has been taken. So allocation with respect to P0, P1, P2, P3, P4 is given. Max is also given and available is also given. So from allocation and max you have to calculate need. All of you listen carefully. So this is the snapshot of the system at particular moment. तर सिस्टीम मध्ये किती प्रोसेसेस आहेत? 5 प्रोसेसेस आहेत P0 to P4 आणि रिसोर्सेस किती आहेत? 3 आहेत A, B, C. आणि A चे किती इन्स्टन्सेस आहेत? 10 इन्स्टन्सेस आहेत. B चे किती आहेत? 5 आहेत आणि C चे किती? 7 आहेत. ओके, सो फर्दर इफ यू कन्सिडर प्रोसेस P0, सो P0 ला किती रिसोर्सेस अलोकेट केलेले आहेत सध्या सिस्टीमनं? A चे 0 अलोकेट केलेले आहेत, B चे 1 अलोकेट केलेले आहेत आणि C चे 0 अलोकेट केलेले आहेत. सो दॅट्स व्हाट इज 0 1 0. And what is the maximum need of process P0? So process P0 ला जर complete व्हायचं असेल तर P0 ला A चे 7 instances लागणार आहेत, B चे 5 लागणार आहेत आणि C चे 3 लागणार आहेत. So that's why in front of P0 under max, so it is 753. Okay, so like that process P1, what is the allocation, current allocation by the system to P1? 2 instances of A are allocated and 0 instances of B and 0 instances of C. And what is the maximum need of P1? 3, 2, 2. 3 instances of A are required, 2 instances of B are required and 2 instances of C are required. Right? So like that, this is the allocation, this is the maximum need of each and every process. And what is the available with the system? So available right now, 3 instances of A are available with the system, 3 instances of B are available with the system and 2 instances of C are available. Right? A चे किती instances system कडे available आहेत सध्या 3 आहेत, B चे 3 आहेत आणि C चे 2 आहेत. Okay? So now you have to calculate first of all need. So how to calculate need? Need is equal to max minus allocation. Max minus allocation. So if you are looking over here, so I calculated the need table here, need column. So max 753 minus 010. So here you have to do the subtraction with respect to the resource type. Okay, so in max the resource type A is having 7 and in allocation resource type A is having 0. So that's why 7 minus 0, that is 7. 5 minus 1, that is 4. 3 minus 0, that is 3. Yes, are you getting my point? Yes, students? Hello?
Yes.
Okay, so in the same fashion, I calculated the need with respect to P1. So P1's need is 1, 2, 2. How it came? That is 3 minus 2, it is 1. 2 minus 0, it is 2. 2 minus 0, it is 2. In the same fashion for P2, so 9 minus 3, 6. 0 minus 0, 0. 2 minus 2, 0. For P3, 2 minus 2, 0. 2 minus 1, 1. 2 minus 1, 1. It's 0, 1, 1. And P4, max is 4, 3, 3. And allocation is 0, 0, 2. So 4 minus 0, 4. 3 minus 0, 3. And 3 minus 2, 1. So that is the need. So I calculated the need over here. And now, after need, so I have to follow the algorithm. Okay. So algorithm tells me that first step is you have to assign available to work. Okay, so assign available to work. Okay, so listen carefully to understand the concept. पहिल्यांदा काय करायला लागणार आहे आपल्याला? So you have to assign work is equal to available. So what will the work? Work will be 3, 3, 2. Okay. So second step, find an I such that finish of I. आता इनिशियली कुठलीच प्रोसेस कंप्लीट झालेली नाही, त्यामुळं सगळ्यांचा फिनिश फॉल्स लाच असणार आहे. That is finish of 0 is equal to false, finish of 1 is equal to false, finish of 2 is equal to false, finish of 3 is equal to false and finish of 4 is equal to false. Okay, so the first condition will be true with respect to each and every process. So we have to think about the second condition. Second condition is need of I less than equal to work, and work is 3, 3, 2. So can anybody tell me which process I am able to choose? So can I choose process P0? Come on.
No, ma'am.
We can't choose process P0 because its need is 743, which is greater than 332. So corresponding digit we have to compare. Okay, so 7 is greater than 3, 4 is greater than 3, 3 is also 3 is greater than 2, 3 is also greater than 2. It means need is greater than available, so we can't satisfy the need of process P0. So that's why in our safe sequence process P0 will not comes, right? Again go ahead. So try to consider the second process. Second process need is 1, 2, 2. So 1 is less than 3, 2 is less than 3, and 2 is also less than equal to 2. So can we consider process P1?
Yes, ma'am.
Can we consider process P1?
Yes, ma'am.
Yes. So we can choose in our shape sequence first process as a P1. Okay. So we'll write process P1 as a first process in the shape sequence. So now process P1's, listen carefully here to do the calculation. So work is 3, 3, 2 and its need is 1, 2, 2. So what you have to do? You have to subtract 1, 2, 2 from 3, 3, 2. So after subtraction, that is 1, 2, 2. So available, that is work will become now 0, 3 minus 2, 1 and 3 minus 1, 2. So you have to subtract the digits. Keep in mind, इथं आपण decimal subtraction करत नाहीये. Corresponding digit मधून खालचा digit minus करतोय. So 3, 3, 2 minus 1, 2, 2. So the result will be 2, 1, 0. Right? So available, that is work will become now 2, 1, 0. And how many we allocated totally to process P1? Come on. आता P1 ला आपण त्याची नीड भागवली P1 ची. P1 ला अगोदर किती अलोकेट केले होते? 2, 0, 0. आणि आता त्याची अजून नीड किती होती? 1, 2, 2. म्हणजे त्याची अगोदर त्याला 2, 0, 0 दिलेले होते आणि आता अजून जे एक्स्ट्रा लागणार होते ते पण दिले. म्हणजे we given everything to process P1, right? So what is the work of process P1? So as process P1 is satisfied with its maximum need, so it goes for completion. And how many it will releases? Can anybody tell me? P1 किती रिलीज करेल कंप्लीट झाल्यानंतर?
7.
See, 3 resources are there. 3 resources are there. A, B, C. तर A ची किती रिलीज करेल, B ची किती रिलीज करेल आणि C चे किती रिलीज करेल तो?
3, 2, 2.
गुड. 3, 2, 2. आपण त्याला टोटल किती अलोकेट केले बघा, तुम्ही कॅल्क्युलेशन करा. त्याचे अलोकेशन आहेत 2, 0, 0 आणि त्याची नीड आहे 1, 2, 2. जर अलोकेशन आणि नीड तुम्ही जर ऍड केला, सो इट बिकम्स मॅक्स, राइट? इट बिकम्स मॅक्स. So as maximum need is satisfied, so what process P1 will do? Process P1 will go for completion, and after completion what it will do? It will releases all the resources. एकदा प्रोसेस कंप्लीट झाली की प्रोसेस काय करणार आहे? सगळे जेवढे अलोकेट केले होते त्याला रिसोर्सेस ते सगळे रिलीज करणार आहे. मग त्याला किती आपण टोटल अलोकेट केले? 3, 2, 2 अलोकेट केले होते. त्यामुळे प्रोसेस P1 कंप्लीट झाल्यानंतर काय करणार आहे? 3, 2, 2 रिलीज करणार आहे. आणि हे रिलीज झालेले रिसोर्सेस आपल्याला कशामध्ये ऍड करायचे आहेत? परत अवेलेबल मध्ये ऍड करायचे. तर आपला अवेलेबल होता 210. आपला अवेलेबल होता 210. आय होप यू आर अंडरस्टँडिंग. येते लक्षात? येस स्टुडंट्स?
Yes, ma'am.
हा, पहिल्यांदा किती होते अवेलेबल सिस्टीम कडे? 3, 3, 2 होते. त्याच्यातले आपण अलोकेट केले 1, 2, 2 आणि ते 1, 2, 2 अलोकेट केल्यानंतर राहिले किती सिस्टीम कडे? 210. आणि त्या 210 मध्ये आता P1 न रिलीज केलेले 3, 2, 2 ऍड होणार, राइट? सो नाउ द अवेलेबल विल बी 2, 3 and 5. So that is 5, 3, 2. So 5 instances of A will be available, 3 instances of B will be available, and 2 instances of C will be available, right? After, that is after completion of P1, this is the situation, right? Before completion of P1, available was 3, 3, 2. After completion of P1, available is now 5, 3, 2. So as available is 5, 3, 2. So which next process we are able to choose? Now available is 5, 3, 2. Which will be the next process we have to choose in the safe sequence? Come on. Yes.
3.
Process P3. Good. Process P3. We can't choose process P2 because P2's requirement with respect to A is 6. Actually P2 ची रिक्वायरमेंट काय 600 आहे. त्याला 6 ए रिसोर्स टाइपचे 6 इन्स्टन्सेस लागणार आहेत, पण आपल्याकडे अवेलेबल आहेत 5च. So that's why we are unable to choose P2. So that's why we are choosing P3. That's why we are choosing P3. So P3's need is 011. P3 ची नीड किती आहे 011 आणि आपल्याकडे अवेलेबल आहेत 532. तर आता आपण काय करणार आहोत, आपल्या सेट सिक्वेन्स मध्ये P3 राईट करणार आहोत आणि P3 ची नीड आहे 011. तर ते 011 आपल्याकडे जे काही अवेलेबल आहे त्याच्यातनं मायनस करणार आहोत. सो 011 सो म्हणजे मायनस करणार आहोत म्हणजे ते आपण P3 ला देणार आहोत. सो नाउ माय अवेलेबल ऑर वर्क बिकम्स, सो 5 minus 0, 5, 3 minus 1, 2, 2 minus 1, 1. So my work becomes now 5 to 1. 5 to 1 and I have allocated 0, 1, 1 to process P3. आणि अगोदर किती allocate केले होते प्रोसेस P3 ला 2, 1, 1. ऑलरेडी त्याला 2, 1, 1 allocate केले होते आणि आता किती allocate केले आपण 0, 1, 1. म्हणजे टोटल किती allocate झाले P3 ला
2, 2, 2.
गुड 2, 2, 2. म्हणजे P3 ला किती allocate झाले टोटल 2, 2, 2. So it was the maximum need of process P3. So what now process P3 will do? Process P3 got its required one. So P3 also goes for completion. And after completion, what it will do? It will releases all the resources. So how many resources it will releases? प्रोसेस
Two, two, two.
कंप्लीट झाल्यानंतर किती रिलीज करेल
2, 2, 2.
2, 2, 2.
2, 2, 2 is 2 instances of A, 2 instances of B, 2 instances of C, and these released one will be again added in the available one, and the available one after P3 was 5 to 1 and now released one are 2, 2, 2. So I will add it and now my available or work will become 5 plus 2 7, 2 plus 2 4 and 1 plus 2 3. Okay, so 7, 4, 3. Now the available is 7, 4, 3. So which process I am able to choose? 7, 4, 3. आता पुढची सिक्वेन्स मध्ये कुठली प्रोसेस आपण पुढची चूज करू शकतो? Come on. Our available is 7, 4, 3.
P4.
7, 4, 3. So you can choose P4. You can choose P0, right? You can choose P2 also. कुठलीही प्रोसेस चूज करू शकता कारण ह्या तीनही प्रोसेसची जी नीड आहे ती आपल्या अवेलेबल पेक्षा लेस दॅन इक्वल टू आहे. So either you are able to choose P4 or you are able to choose P2 or you are able to choose P0. Okay, so if we follow first come first serve or the same sequence, so we'll choose P4. So P4's need is 431. 431. You will subtract it from this available. So now the work or available becomes, so 7 minus 4 it's 3, 4 minus 3 it's 1, 3 minus 1 it's 2. So now the available is 312 and we allocated 431 to process P0 and initially process P4 was having 002. So total 433 we allocated to process P4. Process P4 goes for completion and releases 433. And the released one again we are going to add in the available one. So 433 will be added and now the work will become again 745. Again the work will become 745. So now, so after P4, so I am able to choose Again, I will follow the round robin fashion. So I will choose P0. So P0's requirement is 743. So I will subtract again 743. So the result will be 002. So now only one process is remaining in the system after P4. The remaining will be 002, and after P0, so P0 will release as 753. So I will add this 753. So the available will be 7, 5 and 5, and I will choose the last process, and the last process is P2, and P2 requires 600. I will subtract 600 from the available, so it becomes 155, and after completion of P2, so it will release as 902. So 155 plus 902. So finally I will get 10, 5 and 7. And initially also with me, the resource type A was having 10 instances, resource type B was having 5 instances, and resource type C was having 7 instances. Okay, so like that I got the save sequence P1, P3, P4, P0, P2. Okay, so I will actually, while I was discussing with you, I have done the calculation on one page, so I will post this page on our group. So this is one save sequence, keep in mind. Okay, so just a minute. Arya, okay, so I will post this calculation on the group, and in the same fashion मी जसं कॅल्क्युलेशन केलंय तसंच तुम्हाला कॅल्क्युलेशन करायचंय आणि सेफ सिक्वेन्सेस फाइंड आउट करायचे. So just a minute, I will post this calculation. मी जसं कॅल्क्युलेशन केले तसं तुम्हाला कॅल्क्युलेशन करायचंय आणि या कॅल्क्युलेशन मध्ये तुमचे जेवढे इन्स्टन्सेस अगोदर होते तेवढेच इन्स्टन्सेस फायनल कॅल्क्युलेशन मध्ये यायला पाहिजे. ओके, so I will save and I will share with you. Okay, so I have posted it on your group, just check it. Yes, got it? Yes, students. Hello.
Yes, ma'am.
So look at to that calculation, how I have done that calculation, and like that, what you have to do? तुम्हाला काय करायचंय? आता आपण एक सेफ सिक्वेन्स कॅल्क्युलेट केलाय, तर किती प्रोसेसेस आहेत? 5 प्रोसेसेस आहेत. आता आपण मागच्या एक्झाम्पल मध्ये बघितलं होतं 3 प्रोसेसेस होत्या, तर सिक्वेन्स किती आले होते? 6 सिक्वेन्स होते, आणि त्या 6 पैकी एक सेफ होता आणि उरलेले 5 अनसेफ होते. तर आता इथं 5 प्रोसेसेस आहेत. So now it's the challenge to you. You have to calculate the safe sequences. 5 आहेत म्हणजे कमीत कमी you may say that with respect to एका प्रोसेस पासून जर स्टार्ट केलं आपण, जर P0 पासून सिक्वेन्स स्टार्ट केला तर ऑलमोस्ट 5 सिक्वेन्सेस येतात, राइट? And here 5 processes are there, so almost 25 sequences are there, and from that 25 we have to find out the safe sequences. Yes, got it? Yes, students. Hello, are you listening to me?
Yes, ma'am.
ओके. आता आपण एक सिक्वेन्स कॅल्क्युलेट केलाय जो की मी तुम्हाला पोस्ट केलाय. तर मला अजून काही सिक्वेन्सेस फाइंड आउट करून सांगा. सो इन द सेम फॅशन यू हॅव टू डू द कॅल्क्युलेशन. आणि कॅल्क्युलेशन कम्प्लीट झाल्यानंतर फायनली तुमच्या कॅल्क्युलेशन मध्ये काय यायला पाहिजे? 10, 5 आणि 7च यायला पाहिजे. का तर टोटल ए चे किती इन्स्टन्सेस आहेत सिस्टीम मध्ये? 10 आहेत, बी चे 5 आहेत आणि सी चे 7 आहेत. त्यामुळं तुमचं कॅल्क्युलेशन केल्यानंतर जर लास्टला 10, 5, 7 येत असेल तरच तुमचा तो सिक्वेन्स करेक्ट असणार आहे किंवा सेफ असणार आहे. आणि जर तुम्हाला वेगळं कॅल्क्युलेशन येत असेल तर वेगळं कॅल्क्युलेशन येणारच नाही आपल्याला. So that indicates unsafe. So come on. So at least one sequence you can find out which is safe. It's a very interesting example. So those who understood, they are able to solve it. So let me check who will solve this example, who will tell me the one more safe sequence. There are total 25 sequences. Out of that, few may be safe. Again, I am unable to tell exactly how many will be safe. It depends upon the example. To find out the safe sequence, one we have already calculated, that is P1, P3, P4, P0, P2. So you have to calculate another one. Should not calculate the same one. So first of all, try to understand how we have done it. So this is the execution of your safety algorithm. Yes, students, are you calculating? If you are not getting, you can ask me, I will repeat. If you understood, you can go ahead, calculate another safe sequence. So Rahul Garpat posted P1, P4, P1, P4, P3, P0, P2. Rahul, post your page where you had done the calculation. You have to do the calculation along with that sequence. जो काही sequence केलेला आहे तुम्हाला, you have to post the page of the calculation. You have calculated orally, don't calculate it orally. So do it on paper. Do it on paper, take photograph of that paper and post it on the group. So unfortunately, your exam is online, but if it may be mostly for offline exam, this question was asked for 10 marks to calculate one of the safe sequence using safety algorithm, using Banker's algorithm. अनफॉर्च्युनेटली मागच्या वर्षापासून तुमची एक्झाम ऑनलाईन व्हायला लागली आहे. तुम्हाला लिहायची काही गरज पडत नाहीये, पण जेव्हा ऑफलाईन एक्झाम व्हायच्या, 100 मार्काचा पेपर असायचा, त्यातले बऱ्याच वेळेला हा कंपल्सरी क्वेश्चन असायचा, फ्रिक्वेंटली आस्क्ड क्वेश्चन असायचा. सो कॅल्क्युलेट द सेफ सिक्वेन्स विथ द हेल्प ऑफ बँकर्स अल्गोरिदम. Come on, students from A division, B division. Nobody from B division is answering. त्याचं घे ना मग. काय झालं? तिला मोबाईल दे की. Anybody has calculated the shape sequence? If you have completed, post it on the group. Yes, anybody has completed? Are you solving? I'm waiting over here. Yes, students?
Yes, ma'am. 2 minutes. Yes. Vedangi posted P1, P3, P4, P2, P0. Good.
3, 2, 2. So at last you got 10, 5, 7. Good. So Vedangi has posted one more save sequence. So I will post it on both the groups. Good, Vedangi. Others. Those who are present. Kriti Adat, Neha Gadge, Pallavi Jadhav, Shweta Jadhav, Sneha Maskar. Sneha Maskar, you are not answering nowadays. Sneha Maskar is there?
Yes, ma'am.
Are you calculating?
Yes, ma'am.
Post it. Yogeshri Pawar, Pratiksha Pethe, Sakshi Shivcharan, Saloni Upase, Aparna, Rupali Jadhav, Anisha Kamble, Neha Kosti, Shraddha Parkipalli, Kiran, Ankita, Vishal, Suraj. So anybody can post save sequence. Good. Sneha Maskar posted P1, P3, P0. Good. Very nice. You are understanding the concept. So third save sequence posted by Sneha Maskar. It is posted on B group. I will post it on A group. Next. See, n number of save sequences are coming. You can post either one. Vedangi has posted one. Sneha Maskar posted another. P1, P3, P0, P2, P4. Rahul has posted one more. Okay. 10, 5, 7. Good. So your result should be 10, 5, 7. Whatever available resources are there. P1, P4, P3, P0, P2. So anybody else? Okay, so 4 sequences we got. So I will post Rahul's sequence. He has posted on A group. I will post it on B group. So these are the samples. Out of 4 save sequences we got. So few more are also there. So anybody want to post it, you can post. And all of you, so whatever sequences I shared, so you can just note it down in your notebook. Okay, so these are the samples. So from 3 students I received Vedangi, Sneha Maskar, Rahul Gapar. So other students, I'm expecting the same from you people. If you are listening carefully, it will be possible for you to post few more sequences. It totally depends upon you. If you are listening carefully, you will be able to understand. That's a guarantee. Come on. Shubham Shende is there. Anisha Kamble, Kiran Aigale. Are you listening?
Yes, ma'am.
So why you are not
Yes,
responding?
ma'am.
Why you are not responding? Unnati Daigude. Swagati Kashid, Aishwarya Kulkarni, Aishwarya Mohikar, Madhuri Dongre. So in second year, you were giving me very good response, and nowadays you are not giving any kind of response. Why you are not giving? So it indicates that you are not listening carefully to my lectures. Only few students they are answering. Vedangi, Rahul, again Sneha Maskar. She was keeping mum from last 3 to 4 lectures, and today I asked again. She replied. So it should not be there. So you should be interactive every time. Come on. Anybody has solved? Anybody got one more shape sequence? Nobody is going to post. If anybody is having doubt, they can ask. Otherwise, we'll go ahead. So total 4 sequences we calculated. I have calculated one. Rahul has calculated another one. Vedangi and Sneha Maskar, they calculated 2 more. So total 4 shape sequences we calculated. Till there are almost 5 to 6 shape sequences, because total number of sequences are 25 as 5 processes are there. So out of that, minimum 10 will be shape sequences. So try it out furthermore. So we'll with this, I can say that you understood the concept of shape sequence according to the SETI algorithm. So hope you have noted it down. Have you noted the algorithm? Yes, students. Rahul Gupta has posted one more sequence. P1, P4, P3, P2. So last you have not written the last process name. P1, P4, P3, P2, and P0, right? Rahul? Yes, Rahul?
Yes, ma'am.
In the sequence, you have missed to write last process name, P0.
Yes, ma'am. Yes, yes.
Complete that bracket also.
Yes, ma'am.
And post once again so that I am able to post on the other group.
Okay, ma'am.
Okay, so total 5 sequences are over. Okay, so hope with this I can say that you understood the concept of set sequence, how we calculated with the help of safety algorithm. Okay, so this is about safety algorithm. Now we'll go ahead. So that is we discussed safety algorithm, and the last algorithm under the bankers algorithm, that is resource request algorithm, is remaining. So we'll see that also. Before that, let me share the sequence posted by Rahul. Rahul, again, you have taken the photograph in such. Okay, it is there. So I will post the last sequence shared by Rahul on B group. Okay. So all the students, if you are not getting it, you can at least note it down. Just go through it. You will understand. If you are not understanding, you can ask me personally also. So we'll go to the second algorithm under bankers algorithm, that is resource request algorithm. We completed safety algorithm. Actually, here once again I have just noted it, the points which we discussed under deadlock avoidance. We discussed the concept of safe state. Then we discussed the first algorithm, resource allocation graph algorithm, with the concept of claim age. Then we were talking about the banker's algorithm, and under banker's algorithm, with the help of example, we discussed about the safety algorithm, which is the mean algorithm. And now we are discussing about the second algorithm, resource request algorithm. So this is about resource request algorithm. So let request of I be the request vector for process Pi, and that request of I of resource type J is equal to K. It indicates that K instances of resource type J may be requested by process I. Then process I wants K instances of resource type Rj. When a request for resource is made by process Pi, the following actions are taken. Okay, so here along with the four previous data structures. So four previous data structure, in the sense we discussed available, allocation, max and need. So along with these four data structures, one more data structure is used by this algorithm, that is request. So this is the fifth data structure. These five data structures are used under this resource request algorithm. We'll see the algorithm. So first step, if request of I is less than equal to need of I, go to step 2. Okay, so this is step 2. If request of I is less than equal to available, go to step 3. Okay, so what we are doing? So we are calculating the request, we are checking the request, and we are checking that request whether it is less than equal to need, as well as whether it is less than equal to available. Actually available resources असणार आहेत, allocation दिलेलं असणार आहे, max दिलेलं असणार आहे, आपल्याला नीड कॅल्क्युलेट करायची आहे. Though process Pi specifies the max, but at the time of execution that process may needs some more, may request some more also. Listen carefully to understand the concept. आता सेफ्टी अल्गोरिदम मध्ये आपण काय अज्युम केलेलं आहे? सेफ्टी अल्गोरिदम मध्ये असं अज्युम केलं की काहीतरी रिसोर्सेस अवेलेबल आहेत, काहीतरी अलोकेट केलेले आहेत, आणि काहीतरी मॅक्सिमम नीड आहे त्या प्रोसेसची, आणि त्याच्यावरून आपण मॅक्स मायनस अलोकेशन वरून आपण नीड कॅल्क्युलेट केलेली आहे. So like that onwards. But over here we are assuming that though I specified the maximum need initially, म्हणजे इनिशियली मी असं म्हणू शकते की I am a process, and initially I may say that I want 10 resources. I want 10 resources. But if the system is not having all 10, so I will not say that give me 10. सिस्टीम कडे जर 10 अवेलेबलच नसतील तर मी म्हणणार आहे का त्या सिस्टीमला मला 10 पाहिजेच म्हणून? नो. सो व्हॉट आय विल डू, अकॉर्डिंग टू माय नीड, अकॉर्डिंग टू माय करंट नीड, आय विल मेक द रिक्वेस्ट. म्हणजे मला 10 लागणार आहेत, मला मे बी सध्या 2 दिलेले आहेत, मी थोड्या वेळानंतर 2 मागेन, त्याच्यानंतर अजून 2 मागेन, त्याच्यानंतर अजून 4 मागेन, राईट? लाईक दॅट. अँड दिस इज कॉल्ड एज अ रिक्वेस्ट. आर यू गेटिंग माय पॉइंट? So I need to request based upon the need and availability, right? So that's why this request is made by the process in between. So max is made by the process initially, and based upon that max and based upon the allocation done by the operating system, need is calculated, and request is done by the process in between. That is while the process is going on, while the process is going on. So though process has requested its maximum need as a 10, but right now it is in need of 2. त्याला भले 10 लागणार आहेत, पण ते 10च्या 10 आता लगेच लागणार नाहीयेत, आता सध्या तरी 2 लागणार आहेत, आणि थोड्या वेळानंतर मे बी अजून 8 लागतील, लाईक दॅट. So this is called as a request. So my maximum need is get divided in terms of request. मला 10 मॅक्सिमम लागणार आहेत, त्या 10 पैकी आता 2 लागणार आहेत, अजून अर्ध्या तासानंतर 4 लागणार आहेत, आणि अजून 1 तासानंतर 4 लागणार आहेत. म्हणजे टोटल किती झाले माझे? 10. Are you getting my point? So the maximum request, maximum need, max is divided in terms of request. Max is divided in terms of request, and according to that request I need to check whether that request is less than equal to need, whether that request is less than equal to available. Then only I have to go to the step 3. And what is the step 3? So we have the system pretend to have allocated the requested resources to process Pi by modifying the state as follows. That is available is equal to available minus request, allocation is equal to allocation plus request, नीड इज इक्वल टू नीड मायनस रिक्वेस्ट. म्हणजे मला थोडक्यात काय करायचंय, माझी जर रिक्वेस्ट नीड पेक्षा पण लहान असेल आणि अवेलेबल पेक्षा पण लहान असेल तर मला ती रिक्वेस्ट ग्रँट करायची आहे. And I will give that requested number of resources to the process. So as I am allocating request to the process, so that request should be subtracted from the available and it should be added into the allocation. The request grant kartoy म्हणजे what operating system is doing. So the request is granted by the operating system in the sense that request will be get converted into assignment. That means number of assignment resources will be allocated to the process. So that's why allocation is equal to allocation plus request, and the need is also get decremented. So need is equal to need minus request. If the resulting resource allocation state is safe, the transaction is completed and process PI is allocated its resources. The resulting state the safe asset, so whatever processes I am choosing, so accordingly I will decide the state. I will decide the safe sequence. So I will decide the safe sequence, and if the safe state is safe, so I will complete the transaction, and I may say that the system is in safe state. Okay. So like that again here, if this new state is unsafe, the PI must wait for a request of I and the old resource allocation state is restored. जर एखाद्या प्रोसेसची रिक्वेस्ट नीड पेक्षा कमी नसेल किंवा अवेलेबल पेक्षा कमी नसेल, so what it indicates, so system is going into the deadlock state. So what that process have to do, that process have to compulsorily wait, right? So this is about the resource request algorithm. Okay, so you may take the same example also. आताच जरी हे एखादा फॉर एक्झाम्पल आता इथे आपण नीड कॅल्क्युलेट केली होती, जर सेम एक्झाम्पल घेतलेलं आहे आपण तुमच्या समोर मला अंडरस्टँड होण्यासाठी. तर याच्यामध्ये आता फॉर एक्झाम्पल अवेलेबल आहे 332, अवेलेबल आहे 332, आणि जर सपोज प्रोसेस P0 ऍक्च्युली त्याची नीड आहे 743, नीड आहे 743, पण जर P0 न जर सपोज 1221 रिक्वेस्ट केलं. Listen carefully, what is the request? Its maximum request is 743, but it has requested 221. It has requested 221. So can I grant the request? Yes. Yes, students, are you listening? Hello. Hello, nobody is listening.
Repeat, ma'am.
Okay, so here I have taken this example. So according to resource request algorithm, resource request मध्ये काय केलेलं आहे, जी काही तुमची मॅक्सिमम नीड आहे ती नीड तुम्ही एकदाच मागायच्या ऐवजी जर ती रिक्वेस्ट मध्ये डिवाइड केली, म्हणजे आता नीड किती आहे 743 आहे, तर 743 न मागता आता लगेच जर प्रोसेस P0 न 221 मागितलं, it means request of process P0 right now is 221. So can I choose process P0 right now?
Yes.
Okay, because 221 it is less than need, that is 743, and it is also less than available, that is 332, right? So I'm able to choose P0. So 221 it is the request, 221 it is the request, and which is less than need as well as available. So operating system is able to grant that request, and after granting that request, so 221 will be get added into the allocation, will be get added to the allocation, as well as it will be subtracted from the available, and as well as it will be subtracted from the need. जे काही 221 आहे, जर P0 न 221 रिक्वेस्ट केला असेल सध्या, तर ती आपण रिक्वेस्ट P0 ची ग्रँट करू शकतो because the available is 332 and need is 743 and the request is less than available as well as need. So as the request is granted, so after granting the request, we need to change the allocation, we need to change the available, and we need to change the need. And accordingly, we can calculate the save sequence. Accordingly, we can calculate the save sequence. So again, it depends upon the process request. So process may request all the resources at a time, or process may request few resources now and few resources afterwards based upon its maximum requirement. Got it? So this is the concept. Yes, students?
Yes, ma'am.
Okay, so here we need to assume the request. So one more data structure we need to use, that is request. So if we add request accordingly, so we need to assume the request, and based upon that request we need to go ahead. Okay, accordingly we need to calculate the save sequence. So it depends upon you. Here I assume the request is 2 to 1 with respect to P0. So instead you may divide the need of P1 also. So right now the P1's need is 122, which is less than available. So we can grant. But if you take 600 आणि जर आपल्याला P2 पासून सुरुवात करायची असेल, so we can divide the P2's need into request. 600 will be divided into maybe 300, 300. So at once one request will be granted, and after some time another request will be granted. Got it? Yes. सेफ्टी अल्गोरिदम मध्ये आपण काय केलं होतं? सेफ्टी अल्गोरिदम मध्ये आपण डायरेक्ट सिक्वेन्स कॅल्क्युलेट केला होता आणि त्याच्यामध्ये काही प्रोसेसेस पासूनच तो सिक्वेन्स स्टार्ट केला होता. पण इथं काय करणार आहोत आपण? इथं आपण अजून एका डेटा स्ट्रक्चरचा यूज करून, so the name of the data structure is request, and we are dividing the need in terms of request. We are dividing the max in terms of request, and we are checking that request whether it is less than available or need. So need may be divided into one request, or it may be divided into more than one request, and accordingly the request will be granted, and accordingly the state will be accordingly the sequence will be decided. So hope you got it. Yes. Yes, students. Hello.
Yes, ma'am.
Okay, so can you take one example? Can anybody will take एखादा एक्झाम्पल घ्या. एखाद्या प्रोसेसची रिक्वेस्ट डिवाइड करा, नीड डिवाइड करा. जसं की मी P0 ची डिवाइड केली होती. P0 ची नीड होती 743 आणि मी नीड डिवाइड केली 2 to 1 आणि 5 to 2, म्हणजे 743 मी दोन रिक्वेस्ट मध्ये डिवाइड केलं. एक 2 to 1 आणि दुसरी 5 to 2, म्हणजे ह्या दोघांची ऍडिशन केली तर 743 येते. राईट. सो आय डिवाइडेड द नीड इन टर्म्स ऑफ 2 रिक्वेस्ट. म्हणजे एकदाच ती नीड रिक्वेस्ट करायच्या ऐवजी प्रोसेस P0 काय करणार आहे? 2 वेळा रिक्वेस्ट करणार आहे. So can you calculate save sequence? Yes.
Ma'am, after dividing the request, can we take the same process one after the other?
Yes. That's why I was in the way to tell the same thing. So in your sequence, same process is coming twice because we are dividing the request. We are dividing the need in terms of request. आता प्रोसेस P0 जर पहिली नीड 2 to 1 भागली, म्हणजे पहिल्यांदा प्रोसेस P0 एक्झिक्यूट केली आपण, आणि थोड्या वेळानंतर परत प्रोसेस P0 एक्झिक्यूट करणार आहोत बिकॉज स्टील इट इज इन नीड ऑफ 5 to 2, राईट.
But can we take immediately?
Immediately it depends upon the available.
Okay.
Is it right?
Means now we have divided P2 as 300. So first I will take 300, then again can I take 300 the second?
Yeah, no problem. No doubt. You can. but it depends upon the available. So available number of resources should be 3, right?
Yes, yes.
So more than once that process will comes in the safe sequence. Okay, so take one of the example. So actually now I'm going to stop over here. So almost we covered the point deadlock avoidance with the help of 3 algorithms, right? Resource request, resource allocation graph algorithm, safety algorithm, and resource request algorithm. So I will give this task to you. So take any example, take any process from this example and divide that process need into maybe 1 request or maybe 2 request or 3 request. It depends upon you. आता आपण म्हणतोय की 2 रिक्वेस्ट मध्ये डिवाइड केलं तर ती प्रोसेस 2 वेळा येणार सिक्वेन्स मध्ये, 3 वेळा डिवाइड 3 रिक्वेस्ट मध्ये जर डिवाइड केला तर 3 वेळा येणार आहे तुमच्या सिक्वेन्स मध्ये, राइट? So you may divide into one request, into 2 requests or 3 requests depending upon the need, and accordingly solve that, calculate the safe sequence. So either you can divide one process request into number of one process need into number of requests, or you may take 2 or 3 processes need into number of requests. It depends upon you. So at least take one process need in terms of 2 requests and solve it so that you will understand the concept. Okay, and we'll discuss again the same thing in the next lecture. So just solve it and keep with you. If you are having doubt, you can ask at any time, and we'll do the discussion on this in the next lecture. So today I will stop here. So almost one point I covered. So only one point is remaining from this chapter, that is recovery from deadlock. So the major from this chapter is deadlock avoidance. I think we discussed deadlock prevention, deadlock avoidance. Yeah, 2 more are there. Deadlock detection is there, and deadlock recovery is there. Two methods are remaining. So we'll discuss these 2 methods in the next lecture. So for a while, this is the part of homework given to you. Again, it depends upon you. If you have listened it carefully, you will be able to solve it. Otherwise, it is again quite difficult. So very few students are listening to me. So hope everybody is listening. They will solve this example. And when they are able to solve this example, if they got the safety algorithm example, हे example जर तुम्हाला कळालं असेल तरच तुम्ही solve करू शकताय. Otherwise, again, it is quite difficult. So we'll see in the next lecture. So drop your roll number in the chat box. Type your roll number in the chat box and you can leave. We'll stop here today.
Ma'am, if we use this resource request, then all the sequences will be safe, right?
Which sequences?
Means if we take any sequence, then it will be safe, right? Because we can divide it.
But again, it depends upon the availability. So sometimes all sequences, we will not say that all sequences will be safe.
Okay.
It depends upon the process. Now, process may request few resources or process may request more resources also. Depends upon the situation.
Okay, ma'am.
आपण अजून करतोय पण असं नसतं ऍक्च्युली रिअल लाईफ मध्ये. एखादी प्रोसेसला जर 10 पैकी 5 पाहिजे म्हणजे पाहिजेच असतात, त्याच्याशिवाय त्याला काही दुसरं काम करताच येत नाही, लाईक दॅट. आणि जर आपण ते 5 परत 2 आणि 3 मध्ये डिवाइड करत असेल तर ते पण म्हणजे त्याचा पण काही उपयोग होणार नाही, लाईक दॅट. डिपेंड्स अपॉन द ऍप्लिकेशन. Yes, Vedangi?
No, ma'am, got it.
Okay, okay.